Okay, so if you're having to watch this lecture from home because you're absent today, it is 12:16. We're going to look at kinetic, various forms of energy, and so this is the content that we're looking at for today. And so the lecture should go over the portions on kinetic energy and then various forms of potential energy. I did have homework out there for you. I think I'm going to have that due for Wednesday because I don't think we're going to finish this content up today. There's a lot of demonstrations that I'm going to do with you, and so demonstrations often take some time. So that homework for Wednesday. All right, let's take a look at it. Objects in motion, they have the ability to, as they slow or stop, to do work. So the concept here is that objects that have the ability to do work have energy. So things that are moving have the ability to do work, and that's called kinetic energy. Now, an object's kinetic energy is equal to the amount of work it can do as it exerts force while stopping. We know Newton's laws say that force is needed to change the motion of an object. So if an object is moving, it takes force to stop it. How much work it takes to exert how much work it takes to stop it is what we call its kinetic energy. Now, in my in Science Olympiad, one of the events right now, and I'm one of the assistant coaches for SL, and so one of the events is wind power, and so I have a turbine set up. These kids are building various types of blades to be able to take wind energy and convert it into electrical energy. Now, we will study electrical energy concepts in the second semester. But come on over for just a moment. I'm going to try to show you the equipment that's set up here. And we'll talk about how this thing is harnessing the energy from the wind. So come on over for just a moment. Again, if you're having to watch this from home, you miss out on some of the demonstrations. But anyway, all right. So this is a voltmeter, and so raise your hand if you've ever done anything with electricity. You know what I mean by volts and resistance. Just a few people. All right. So when we study electricity second semester, you'll see this in more detail. This turbine blade is connected to a DC motor. This motor is part of a CD player. And so instead of using a electrical current to run that motor, we're going to use mechanical energy to sort of make a voltage here. So as this thing spins, Logan can probably see that as this thing is spinning, it's developing a voltage, and it's reading what that voltage is. Now, the faster I spin this thing, the greater that voltage is. Now, we can see that there's some frictional forces acting here. We know that objects should continue indefinitely unless there's some frictional forces acting, and there's definitely some friction acting there. Also, we're generating some electrical current, which means that we're doing some work on the electrical wiring. So that's energy that's going into something else. Now, first, I want you to take a look at the structure of those blades. Wind, we know that air is moving matter, and moving matter can do work, right? So I'm gonna blow Will's hair back. Are you ready? So we've seen this before. And so moving air can do work, and that hair, wait, what is going on here? There we go, a little bit better. It takes some work to be able to do that. Now this thing here, I'm gonna shoot some air at this. Which way is this thing gonna spin based on the air coming in? I want you to look at the size of those blades and the way those blades are shaped. How is that gonna cause that thing to spin? Which way? So take a moment to see if you can tell that person that you're sitting next to, is it gonna turn clockwise or counterclockwise based on the way that those spins are going? Take a moment. What do you think? Counterclockwise? So it's going to spin this way?
Yeah.
How do you know that?
Because the blades are bending.
The blades are bent, yeah. But why would it spin counterclockwise, not clockwise? Just based on the way. How would you sort of describe that? You guys agree the air is going to be deflected by those spins? Which way will it be deflected? When you look at this, the air is coming in like this. It's going to hit these spins. How is that going to be deflected? It's going to be driven sort of that way. Would you guys agree that it's sort of that way? If the air is driven this way by those fan blades, then the fan blades are exerting a force to divert the air that way. So what must the air do? It must exert a force this way, which should cause it to spin counterclockwise. Okay, so how this works is it harnesses the energy of the wind, and moving air, I'm going to try to have this be constant here, moving air should be able to get those things to spin, and you can see that spinning. Now, Logan, I want you to read for me, just harnessing the energy from that wind. What's that reading?
Now
0.6 volts-ish or something. Okay. So the idea there, thank you. I'm just setting this up so you guys can see. You have seen wind turbines on the side of the roads when you drive up north like I go up to Manistee area a lot. You see these big wind farms up there. Those big wind farms that they're just harnessing the energy from them. And so this is an event in Science Olympiad, and their goal is to build within a certain size CD to be able to build and harness as much wind energy as right? That's accomplished. Now they have like 20 different things that they're testing right now, but they're just looking to see how these things sort of work, if you will, pun intended. Work, force, and resistance, and that goes together. Okay, and I'm back to I know, I mean, I tell you, now that we're in physics, I have so many like puns that I can throw your way, which I can tell you guys are super excited. Really funny? I thought you said really funny. That would be even better. All right. Now let's quantify that. Energy. One of our things in physics is that we quantify forms of energy using mathematical models. So here is the model for us. And so how we define kinetic energy, whether or not you write that as E sub k or ke, I write it as ke, but this right here is just the mathematical model for kinetic energy. We take 1/2 the mass of an object, multiply it by its speed squared. Now this is kinetic energy. It is a scalar quantity. Scalar means no direction associated with it. So it's scalar. No direction. Kinetic energy, fairly easy to work with energy principles as opposed to vector quantities. Vector quantities, we have to worry about which way they're pointed. Kinetic energy, scalar. No energy, no direction associated with it. Now, I'd like to do another demonstration with you, showing you the importance of speed in this equation. Kinetic energy increases with the square of the speed. What that means is if I double my speed, how much more kinetic energy should I have if I'm going twice as fast? Should have 4 times. So it'd be a quadrupling your kinetic energy. So there is a strong dependence on speed. Speed being squared means twice as fast, 4 times as much energy. Tripling your speed, what if you go 3 times faster? It'd be 9 times the amount of kinetic energy. Now, the demonstration I want to do has to do with stopping distance. And this stopping distance idea is something that's critical for you on the highways or on the roadways. When you're traveling twice as fast, you should technically need then 4 times the distance to be able to stop your cars. I mean, that's because kinetic energy is related to the square of the speed, and so is the amount of work needed would be proportional to the square of the speed. So the more kinetic energy you have, the harder it is to sort of stop your car. Now I want to do this demonstration over here by Amelia. So if you would come on up for a minute, I need some space here, if you would. So if you could help me for a few minutes. Come around this table. I'm going to do a little demonstration. Or give me a little bit of space. Yep. Come on. If you're having to watch this from home, just realize that it's so much fun watching these demos. Now, you guys remember the penny activity that I had to have you guys do with the turntable thing? You guys all get those things turned? Yes, I sure. Okay, so I'm going to create a little ramp. Now, here I have all those pennies from your turntable demonstration. What I'm going to do is I'm going to allow friction to be the stopping force here. And would you guys agree friction would take away the kinetic energy of a car? You guys agree? So I'm going to slide this thing down here, and you can see how far that thing slides. Now this is not a perfect model because when it comes off the end of this thing here, it sort of skids a little bit. There, it sort of wobbles around a little bit. But look at the distance that it travels, and that distance that it travels is somewhat consistent. Look at that one. Would you agree that distance that travels is somewhat consistent? Somewhere in that, would you guys agree? It's fairly. Okay. So my goal here is to say, how does the stopping distance relate to the speed? According to this, it says twice as fast it should travel 4 times as far. So my question for you is, how far should if I release this thing from a certain height on this thing here, how high up would I have to go along here to be able to get it to go twice as fast? And they ask you to determine how far up I should make this thing be for it to be twice as fast as this speed. how would I have to change that distance? Turn it on the first thing sit next to, how much I would have to increase the length of this track to be able to make it go twice as fast. Take a moment and turn it on the first. And what would that be? Clearly, I have to go higher up in the track, but how much higher? Double the height? You'd have to go 4 times up on that track. Now, for those of you that are wondering where this is coming from, you guys see equation number 2 up there? V squared is equal to V naught squared plus 2e delta x. Would you guys agree that the acceleration it has on this track should be the same regardless of where it releases it? Right? You guys remember doing that with ball rolling activities? Did we do the ball rolling activities with that? Okay, so the acceleration should be the same regardless of where I put this. But if I want to get the speed to be twice as great, wouldn't I have to make delta x be 4 times as big? So here's a certain speed. This is the 30 centimeter mark. This is the 120 centimeter long track. So if this is 30 centimeters, this is 4 times as far. So what I'd like to do is get a sense as to how far these things are going to skid when friction is what's stopping it. And so here it is coming in with a certain speed v. I'm going to do this like 6 or 7 times, and we just get a sense of how far that thing. Okay, pretty consistent. So those are there. We're going to do that a few times. Brad, help me out. You're going to release this thing from right here, because I don't want people to think that I'm right on this. Watch in here. There you go. All those right there, do it again.
I feel like it counts if you move them.
Okay, do it again. Would you guys all agree that it's pretty consistent? I mean, within some reason, I know friction is one of those. How far did that thing travel? Let's just do this little math here. That traveled about 19 centimeters. Remember that number, 19 centimeters. It came into the skidding with a certain speed. It traveled that far before it came to a stop. Now what we're going to do is we're going to double the speed. We're going to release it from 120 centimeters, not from 30. That equation said it has to get 4 times as far to get twice the speed. All right, now are you ready?
Sure.
Okay, so I'm going to put this right here. This is about where those things went. I'm going to do the first one. So I'm going to release it here. What I do is I sort of set it right in the timer, so it goes a little bit slower. Okay, ready? Maybe it's just I have some magic. See how it's spinning like that? I'm not sure why. Take these 4 and do that again. I'm not sure. Put it with the.
Right here?
Yeah.
That's what I was
There you
doing.
go. Better. I'm
I
not
didn't
sure.
do anything.
Friction is one of those really crazy things. So, okay, that was a little light. There you go. How far was it before? About 19? Let's check it. What is 19 times
38.
19 times 4? 19 times 4.
76.
It's about 76. Now, it looks like they're a little bit shy from that. I mean, there we go. It's about 7.
Perfect.
It's perfect. You guys agree that's about 4 times further? It's about, and that's what I'm trying to do. Is that kinetic energy, the stopping distance is 4 times as far if you're traveling twice as fast. Greta, what is going on with that? Now watch. Every time I do this, watch.
I did not change a single thing from all the times I did it. Nothing's different.
Amelia?
What? I mean,
But because I'm just not sure that Greta is doing this right here.
okay. Where am I putting it?
Oh my gosh, right there. No, wait. Just like that. Nope. See how that thing's spinning?
Oh,
Okay, now try that. What is going on?
we're not penny calibrated, just like I think.
That was horrible. That rolled. Get better.
Maybe just wrong.
Just
right
launch it.
that way.
Applied force. Initial velocity.
I would say, would you guys agree that there's some level of consistency here, except for that? Would you guys?
Ignoring all the inconsistent.
I mean, 4 times as far with twice the speed. Thank you, I'll be here all week. All right. So you're talking about one of these things?
Yes.
Just put it against the wall. Yeah, put it against the wall.
Do what?
Put it against the wall. If you leave the track.
Yeah, you guys make it sound easy. Come here. Come here, you try it. Go, show me how to do that.
Right there.
Talking a lot of trash here. Hey, there we go. That's what you're trying to do?
Yeah.
Go get it. All right, let's end it. Good job. A little demonstration, at least I'm hoping the demonstration was to show you twice as fast, 4 times. You'll stop it. Don't you throw it. Don't you throw it. All right. All right, let's keep going on. If you missed that from home, I apologize. It was a breathtaking demonstration. All right. Now, some other things you've got to look at. The homework that you guys have associated with this is just using these models. Potential energy is, I like to call it potential energy due to position. It has to do with objects that are part of a system of things. So whereas kinetic energy belongs to an object alone, potential energy belongs to a system of objects. We have to have multiple things that are part of the system in order for me to have potential energy. It can be considered stored, and the reason we think of it as stored is that it has the ability to do work or transfer energy when its position changes. Recall PE is force specific. So there are various forms of potential energy. All of them are associated with fundamental forces of nature. So there is a gravitational potential energy. It has to do with the gravitational force. Common form belongs to a system, usually an object and something else. What is the system that gives an object gravitational potential energy? I'm going to have this ball. This ball has energy associated with position. You can release it here, it's got a certain amount of energy. Release it here, has more energy. Release it here, has more still. What is the system that gives this thing energy? You take a moment and tell the person you're sitting next to. What is the system required for this thing to have gravitational potential energy? Go. Objects that are part of the system give it energy. What is the system that gives this thing energy? One of them is a ball. What else? Not a table, thank you. Say it one more time. The Earth is what gives this thing gravitational potential energy. So the Earth is exerting a force on this object called its weight. It's got to have both the object and the Earth. So the Earth is the thing that has to be a part of that system in order for it to have energy. It's equal to the amount of work that we do needed to move an object a distance h in a gravity field. So we know that the Earth is producing a gravitational field called G. And how we find the amount of work that we do when we lift an object is we use our F, work is equal to force times distance. In this case, the force is the weight of the object. So how heavy is it? How heavy it is just m times g. And now what we notice is that d, I'm going to replace that with h, where h represents the height that I'm lifting at. So work, again, force times distance, and that work is what we call gravitational potential energy. So again, when you go to solve problems involving gravitational potential energy, my mass has to be in kilograms, g measured in meters per second squared or newtons per kilogram, and then h would be measured in meters. So how much mass does it have? How high is it? And that's how we calculate the gravitational potential energy. Who wants to check their their energy calibration right now? I'm going to check to see if you can do it. Let the record show no one is raising their hand. Oh, one, we have no one. All right. So now I'm going to release this thing from a certain height. Put your hand out. You're going to catch it. I'm going to release this thing from 30 centimeters. Okay, are you ready? 30 centimeters. Tell me how much. Tell me how difficult it is to sort of stop this. 30 centimeters. Ready? Okay. Now I'm going to release it not from 30. I'm going to release it. Do you feel that? Okay. I'm going to release it not from 30. I'm going to release it from 60. How much more energy? Turn to tell the person that you're sitting next to how much more energy it has at 60 compared to 30. So take a moment. How much more energy it has? Okay, ready? Twice as high. You ready? Can you tell that there was more energy associated with it? How much more energy was it? Not quadruple. Your energy calibration's on. Notice I'm not squaring the height.
Oh.
Right? Whereas I'm squaring the velocity, right? Twice as fast would be 4 times as much. Here I'm just making the height be twice as high, which means I have twice as much energy. What if I take it not 30, not 60, but 90? How much more energy does it have here compared to there? 3 times here, ready? Can you tell that the energy increase? Mm-hmm. Okay. I like it. You're passed. You passed.
Sweet.
Yeah. MGH. All right, our last one that I want to look at, the one that takes the most time to be able to figure out, is this thing called elastic energy. So elastic energy, objects that are elastic, they tend to return to their original shape. So things that are elastic have some relaxed position that objects want to return to. When I change its shape, I can get that energy stored and then get that back. And so I want to look at a variety of things that have what are called elastic energy. So again, the idea behind elastic energy is that objects have natural shapes held together by intermolecular forces, if you will. I had some group do this one here. I don't remember which group it was that measured. Okay, so when you guys did this, you guys calculated how much work it took to be able to bend that thing back a certain distance, correct? You guys did that? Where's the energy stored here? Where am I storing the energy? In what object? What object's storing the energy? The meter stick. You notice that the meter stick has a natural shape that looks like this. When I do some work on it and I can change that shape, I've stored the energy in the shape of that object. When I let this go, you notice that the meter stick wants to go back to its original shape, which means if I've stored some energy, I can get that energy back by allowing this thing to sort of return to its original shape. So here it is me storing work, and then I'm getting that work back when I let this thing go back to its original shape. I need someone that'd be willing to store some elastic energy in this balloon. Just got blown up. Thank you, Joe. Sorry. Now I'm going to do the same thing with this. Now look at your lungs have to do some work on that air to blow that air into that thing and store that in that balloon. Now I'm going to try to get this thing to keep going. I'm going to do the same thing. Keep going. Keep going. That was not supposed to do that. Julian, did you put too much in there? Sorry. Let's try that. Let's try that again. There you go. Try that again. This time don't blow it up too much. That was my fault. That's what it was. Okay, try that again. I'm going to do the same thing. Erase that portion of the video. All right. Julian. Yeah. These things have been sitting in here for a while. Okay.
It's got to be the longest lesson.
I'm not derivative from squared. Sine, 2 sine.
How can you do anything?
Would you guys agree I did some work on both of these things? Yeah. When I let this one go, what's it going to do? When I let this one go, what's it going to do? Why not? What's the difference here? This has a natural shape that's in this configuration. When I change its shape, I'm changing its configuration. I want it to go back to its normal. So I can store some energy in the shape of that. When I do this here, even after a shape, it's not very elastic. When I let this go, what am I doing? Because I'm not storing any energy in its shape. So that's the idea. It has to have a natural shape that it wants to return to. As before, the stored energy is ideally equal to the work done to change its shape. Now, I have some other demonstrations I want to be able to do with you. I want to take this one into the back here. So demonstrations always take some time. In the back table. Back table. Come on back. This one here. All these balloons that are broken all over the place. All right, now, you got me meters. Okay, I want to see how much of the gravitational potential energy this thing retains in this drop. Now, this is a 1 meter stick. When I drop it, you notice that it never quite goes back to the same height from which I release it. Would you guys agree that it's acquiring kinetic energy as I drop it? No. Do you guys agree that it's acquiring kinetic energy when I drop it? If I double the height from which I release this thing, it has, would you guys agree, it has twice as much gravitational potential energy here as it does here? Okay, so I'm going to allow it to bounce back up. You notice that it bounces back here. How high is that in relation here, Nick? How high is that in relation to this? Can you read that?
73.
Would you guys agree it retains about 73% of its gravitational energy? It retains that in the bounce? Okay, if I drop it from 50, how high should it return?
30, 35.
Okay. Pretty close? Drop it from 50. Would you agree that how high it rebounds is a function mostly of how high it comes from? Would you guys agree with that? It's keeping about 75%-ish of its gravitational potential energy. So where's that energy come from? It comes from me it goes from gravitational, it compresses some in its shape. You notice, squeeze that thing a little bit. You notice that it has a tendency to return to its original shape? That means I can store energy in its position. So when I release this thing, I'm storing that energy and it comes back. Now, what I'd like to do is I'd like to get this thing to bounce up to the ceiling. So I'm going to show you guys, I'm going to throw it down, I'm going to try to bounce it, get as close to the ceiling as I can as a little game. Now, anyone willing to go against me on this thing to see if you can get closer than I can? Is you willing to try? Okay, you ready?
Yeah.
Okay, so here we go. Yeah, because we're going to do this together. Are you ready? Okay, 3, go. Try that again. No, just try. Yeah, throw it hard. Looks like this, right? You just gotta throw it down. Oh my gosh, don't do that, right? Try that again. Oh.
What? It's not bouncy.
What do you mean it's not bouncy?
It doesn't have any elastic.
It's the same ball, it is. I mean, it's the same exact same ball.
Let me test it.
Look at it. It bounces. Right? Here, try it. Okay. So the idea behind this is that one is a happy ball and one is a sad ball. So this one can store its elastic potential energy in its shape. This one, feel that, it's not squishy.
Yeah, a little bit.
Right? Feel that. Yeah, so this one, when you change its shape, it just basically stays in its position, right? So that one cannot store elastic potential energy, whereas this one can. And so the idea there, again, is just energy is associated with the shape of the object. Now I have one more. Someone told me, I do have somebody. All right. So unfortunately, have you guys heard of Amazon? I just discovered them like last year. So anyway, I bought this thing. They said that this thing can bounce higher than the height from which it's dropped. But it did not come with instructions, so I don't know how to work this thing. So you guys understand the idea that this one never bounces higher than the height from which I dropped it. Unless I throw it, I can get it. But I just don't know how this thing is supposed to bounce higher, because I've tried this like numerous times. And it It just doesn't bounce higher than the height from which I dropped it. But it didn't come with instructions, so I don't know how this changed.
Another trick, Josh.
Oh, no, seriously, the box, I might still have the box. It doesn't have instructions on it, so, whoa, what'd you do? That is not how, wait, you're throwing it. You're throwing it. Wait, I can get this thing to bounce higher. What did you do?
Flip it inside out. Flip it inside out. So that wants you to make use. I can't tell if you're joking or not.
I'm working on my tell. Because apparently I have a tell. My kids tell me, like, Dad, you can't do this because the kids don't know. You're joking. All right. Now, the idea behind this, would you guys agree that I'm storing energy in a shaker?
Yeah.
So when you do some work on this, right, you do some work, you change the shape of that object. It wants to be like that, correct? So when I do some work, I can store the work that I do in the shape of that object. Now this thing can sit there all day, and it won't go into its other state unless I give it something to sort of trigger. Now, that trigger, I could try to do it like this, right? Tap on that to get it to go. I mean, it can do it, but it's sort of difficult to do. So how do you do this? You drop it from a certain height. So what I'm going to use is the force of collision. You guys remember having to do how much force of collision your egg drop experienced during the dropping? I'm going to use that collision force to sort of activate it. Look how much this thing retains of its gravitational potential energy as a percentage. You guys know. What would you say that is as a percentage? Do you agree it's about 130, maybe 140%? Would you guys agree?
Sure.
Okay, so watch how high this thing goes up in relation to Mike's head. Pretty close to the top of his head, right? If I drop this thing from down here, should it go up to about 150% of the drop height, or will it go back up to Mike's head? Turn it on that person next to you. What will it do? Would you agree? So if I drop it from here, it should go up to about his waist. Okay, ready? Wait a second.
You made it.
No. I'm not tricking. Now watch. Drop it from here. Goes up to about this height.
Drop it somewhere way up there.
I gotta stand on the table on that. Watch it. It goes up to about here. Now if I drop it from down here, you're saying that it should only go up to about 130% of its height. But yet, it still seems to go up to the same. Why is that?
Oh, elastic.
Would you guys agree that this energy depends on the height from which I drop it? Regardless of the height I drop this thing from, the amount of energy it stores is the same, right? So as long as I can drop it from a high enough height to activate it, if I drop it from here, it doesn't activate it. But if I can drop it from a high enough height to get it activated, it converts that elastic energy into essentially gravitational energy. How do I spin it? It's like spiraling into a rubber band, right? When I spiral it, it tends to make it fall more straight, right? If I just drop it like this, it'll fall. And so if it hits at some weird angle, it doesn't go anywhere. So the spinning action, a lot of people are like, well, why do we spin things, right? There's why the quarterback spiral things. It's all about trying to keep it to fly straight, true and straight. Okay, so it's that. Now, this did not come with instructions, but I did know how to.
Okay.
Could you guys tell? Can you guys tell when I'm talking?
No.
Yes.
Sometimes.
Yes.
I'm trying. I'm working. All right. I don't know. 141. What do we go? I just have too much fun with this stuff. All right. So my question for you is this: What are the objects that are part of the system needed to store elastic potential energy? What are the objects? Just like we talked about here, I had to have the Earth and the object be part of the system for me to store gravitational energy. What are the objects involved in elastic potential energy? Could you explain that? Where does that energy come from? Take a moment and tell that person what are the objects involved. So I'm filling in the blanks down at the very bottom. The system. What is the system involved in the ability to store energy in the shape of that meter stick? What's the system? Don't say the meter stick and the string. I'm using the string to be able to do the work to change the shape of that. So, say it again. Then you get a meter stick in the hand. It's not a meter stick in the hand. Look, if you think it's a meter stick in my hand, I can replace it with your hand, pull that thing back. It's definitely not, and then let it go. It's not the hand. The hand is the thing that's doing the work to lift. The hand is the thing that's doing the work to lift this ball, but my hand is not part of the system. My hand is an external force to lift it. It's the earth in the ball that gives that thing energy in this position, right? So what is the system that gives this meter stick energy? That's really the question. What are the objects involved? If you want to get this thing energy stored in that shape. Say it again. So the tension, thank you. The tension in the string is there as a means to change the shape of that object. Instead of using it with string, I could just do this. Would you agree that I'm still storing energy in the shape of that? So the string is just a way for me to be able to do the work on it. To be able to store. The energy comes in the storage of that shape. So where's the system? What's the system involved? It is literally from one molecule that makes up that object to the next molecule. So where this energy comes from, it's molecular in nature. It's one molecule sort of interacting with another molecule to be able to change that shape. So where we get elastic energy has to do with, it's more of an internal energy idea, right? So it has to do with one object interconnected with another. Let me show you a couple of slow motion videos. So let's first do the golf ball being hit. I think I have one that's a golf ball. So for those of you that are golfers, yeah. Okay, so here I want to show you the slow motion of a golf ball being hit. So the ball has a normal shape. All right, come on. Cancel. I just stopped that. Let's go back. Who is Bernoulli? What? Horrible. All right, let's try this again. Golf ball being hit. Okay, so watch the change in shape of this ball as it's being hit. Don't you do that again. Okay, so the ball has a natural shape. When the club hits it, it changes that shape and it stores that energy in its shape. Now, as the ball returned to its original shape, it can sort of give that energy back. And so that allows that ball to come off with a greater speed than if it weren't as elastic. Now, I have another one with a tennis ball being hit. I'd like to show that one here for a second. So tennis ball, slow motion. Okay. Now, this is a 142 mile an hour serve. I'm going to slow it down. This is a 6,000 frames per second. The amount of energy stored in the shape of that ball has to do with what we call elastic potential energy. That racket's coming in and hitting that ball. It basically compresses it into a pancake. And so you can see the shape of that ball changes quite dramatically during that collision. That force is very, very big. It causes that ball to change into a shape of pancake, and then as it rebounds to its original shape, it can give that energy back. So elasticity has to do with, we're storing energy in the shape of that object. And so that ball is going to be able to come out much faster than if the ball was not elastic. Okay, so elastic energy, again, it's a pretty important part of the way we store energy in the shape of objects. Guys, I'm going to stop there. I did not do any calculations with you on elastic energy. I'm going to show you how to do that. A lot of it has to do with that area underneath the force displacement graph. We'll save that stuff for tomorrow. Folks, you have some homework to look at. Not all the homework can be done just yet because we haven't done any elastic potential energy as far as quantifying. Give a go at those things and don't delay for doing all your studying Thursday night because I want to make sure that you guys have this quiz good for Friday. Okay? Have a great day. When the bell rings, you get out of here.